In this class, we're going to look at vectors and the mathematics associated with their use. Now, as we should have discussed before, vectors are really depicted graphically as arrows. The magnitude of a vector, if we're looking at it in a graphical sense, is usually depicted by the size of the arrow. That means in this particular case, vector B is roughly 2 times vector A. Now, bear in mind, if you are writing a vector in an exam or any other scenario, usually sitting and writing multiple vectors and using a ruler and measuring them out can get a little tedious. So unless you're specifically using the graphical method on graph paper to solve your vector system, I tend to just write the magnitude of the vector above each in a simple diagram. Vectors basically show you any property which has both a size and a direction. We're dealing mostly with kinematics in our case, so displacement, velocity, and acceleration tend to be the main points that we use vectors to express. Of course, if we multiply our vector, say velocity, by a scalar, which is a mass, we would get back momentum, which in itself is a vector quantity. The same is true if we look at a force, that being mass times acceleration. So a vector quantity times a scalar gives back another vector quantity. So remember, vectors, they have to be, if they are equal, of the same magnitude and in the same direction. So the direction of our particular vector is very important. And as we discussed in kinematics, keeping our positives and negatives and even the direction of a vector in terms of angle are very important. When we say a vector is equal to another vector, here we're saying vector A is equal to vector B. That means that vector is equal in all dimensions. That means the element in the x direction of A is equal to the element in the B direction. Y to Y, Z to Z. And of course, if we're to look at this way, AX equals BX, AY equals BY, AZ equals BZ. So, two equal vectors are equal if all of their components are exactly the same and their direction is the same. And of course, you can see vector diagrams of this type. If we're to look at the velocity of this vehicle, this cartoon taxi, over 3 different times, t1, t2, and t3, we consider vector as the same length in each case, meaning v1 at t1 is v2 at t2 is v3 at t3. So we can either show this mathematically, or we can, by inspection, look at these vectors and see their lengths. Of course, that's not always the case. If we're looking at an accelerating system, here we start out with a vector of 4 meters per second again, but now at t2, v2 is larger, at t3, v3 is even larger. That means v3 is bigger here than it is at v2, which is bigger than v1. That means we're looking at an accelerating case, and that's useful if we're looking at this in a graphical sense. Usually this would be pretty pointless because we could tell this from the actual readout numbers that we would have. But if we're looking at large vector fields, such as this, here we're looking at the wind speed and direction for our entire planet. So if we're looking at the wind speed, each one of these vectors is showing you the relative wind speed. So here we are looking at the Americas, is India, Europe, Australia, and you can see where the greatest concentration of vectors is, but also the length of the vectors. So here you can see very high wind speeds. Over here you're seeing virtually no wind speeds in the mid-Atlantic to North Pacific areas. So this can be very useful, both in computational sense and in a sense of looking at things just by inspection and telling where the greatest activity is. By contrast, if we're to look at, say, just temperature, or in this case dust loading in an atmosphere, then all we'll see in a scalar is just essentially a size in a particular location. So as we've previously discussed, the directional properties of vectors are particularly useful and allow us to make geometric solutions. Here we have a vector of 5 in the A direction and 2 in the B direction. If we wanted to find the distance after two displacements, so if we take a displacement of 5 meters in A and 2 meters in B, if we want the total displacement from the origin, we would of course have to find the resultant vector r from the origin to this point. That means we would want to find this side of a relatively simple 90-degree triangle. And that means frequently employing the same old trigonometry that you should already have seen previously. So the solution in this case would be to use the tangent here of this angle, and say tan theta is 2/5. So fall back on your normal trigonometry, usually taking your vectors like this and figuring out a 90-degree triangle is not particularly difficult. If you are doing 16 sides of algebra in this class, or 16 sides of trigonometry to solve a single problem, you're probably doing it wrong and should probably return to the original question and think about it a little more. That's not to say everything will always be a nice 90-degree triangle that you can apply a sine, cosine, and tan to. You may, of course, have to resort to Pythagorean theorem here. So in these particular cases, we have our vector ax, here's ay, and here's a vector a, here's the components. So vector a here will have components ax, ay. Ax will be equal to a cos theta, the projection of this vector onto this axis, and ay, the component in the y direction, will be the projection of this vector onto this axis. So a sine theta. Consequently, the magnitude of a would be a squared, which would equal ax squared plus ay squared, or a will equal the root of ax squared plus ay squared. Or at least the magnitude of the vector will. So the magnitude of any vector is the square root of the sum of the squares of its components. So if we want to find out the magnitude of vector a here, we will sum a in the x direction, a in the y, a in the z direction squared, root them out. Quite frequently I'll use the to the power of a half notation instead of this root, especially in PowerPoint, which is a little clunky with its roots. So that's another method that's frequently used when dealing with vectors. So remember, in terms of our vector addition, and we've seen this before, your scalars are added up normally. 10 plus 10 is 20 here, but in vector addition your direction has to be considered. So here 4 plus 4 is 8, 4 plus negative 4 is 0. There's still a total net force of this total force here of 4 newtons going in each direction, so a total force of 8 newtons is still present here. It's just now 4 newtons is this way and 4 is this way, giving us a total force of 0, for instance. We could have 6 in one direction, negative 2 in the y would give us 4. So when you're adding vectors, of course you can have two disparate vectors which are not in contact or interacting with one another, and they will both have elements in the y and x directions. They will both have components in x and in y. So if ax equals bx, then ay equals by, then these two vectors will be equal. A will be equal to b. So given two vectors, a and b, the resultant will be the resultant vector of the two components. R will be a and b together. That doesn't mean you just sum them together. We of course could use, say, Pythagorean theorem there, but there'll be some sum of those two vectors. But if you do sum two vectors, A and B, that means you have to collect the x component with the x component of B, the y component of A with the y component of B, and the z component of A with the z component of B. You cannot, for instance, go AX plus BX, AX plus BY, AX plus BZ. You must only add the components that are in the same direction. X's go with X's, Y's with Y's, Z's with Z's. So quite frequently you can call this, say, the parallelogram rule when adding vectors together. When we're looking at vectors, vectors are always added in a commutative fashion. In this particular case, what we're saying is A plus B here would be B plus A. Or if we take A and add it to B, which add it to C, then A plus B plus C is the same as A plus B plus C. So in terms of our vector addition, here we have vectors A and B. The resultant A plus B will be this vector here, which often gets called, in this case, vector C. We could, of course, applying the parallelogram rule, you could, of course, see the symmetry in this situation and equally say that B and A here would be equal to B and A here. So R is equal to A plus B is equal to B plus A. And that's fine for adding vectors in any particular combination, and that can be used for multiple systems of vectors. So far all we've done is look at two vectors, but say we have vectors A, B and C here. We could, in some cases, want to know what's the resultant vector of A, B and C. Sometimes we might just want to know what B plus C is. So B plus C can be evaluated here, and then we can look at A plus B plus C. Likewise, here we have vector A, B, C again. We could look at A plus B or A plus B plus C. Finally, here we have vector A this direction, B, and now C comes back in the direction of A. So this would be A plus B plus C from here to here. If three or more vectors are added together, then their sum is independent of how you group them. That's referred to as the associative law of vector addition. So A plus B plus C, as we said, is B plus A plus B plus C. Of course, subtracting vectors is the typical algebra we've always used, typical methodology. So A minus B, in a lot of cases, can be written as A plus, a summation, of negative B. This can be quite useful if you like to hold on to the sign of your particular vector. Remember, the sign of the vector is its direction, and it's quite often that you want to make sure you know which vectors were going in which direction. So you're not simply summing or subtracting, I should say, two vectors just because you want to subtract them. You are actually taking into account the physical nature of B. So quite often I will actually say A plus and then have just negative B here in brackets to remind me that B was in the negative direction. So the subtraction of B from A is equivalent to adding negative B in A. So C, if vector C is A minus B, this can be A plus minus B, which should be relatively obvious. So when subtracting vectors, A minus B is A plus minus B. And this kind of shows us what that would look like in a graphical fashion. So here we have the resultant of A minus B, here's negative B, here's A. So what about multiplying vectors? So we've mentioned a couple of times now that we could look at, say, momentum in physics, P equals mv, or forces, F equals ma, when we multiply our scalar, m, by either v or a vector quantity, we get back a vector quantity. As such, if we take a scalar and multiply it by a vector, all we really do is scale up that vector. We don't change the nature of the vector, we just make it bigger, or if we multiply by a fractional value, make it smaller. So here, c times a, if we multiply a scalar by vector a, we will multiply the scalar c by x, y, and z equally. So we'll have c times ax, c times ay, c times az will be equal to ac. If, for some reason, we multiply the vector and we end up with a negative value, then what we're seeing is a reversal of the vector. So if c was equal to -1, we would get negative a back, and that would give us a vector in the opposite direction than we had initially. As you can imagine, if we were talking about p equals mv or f equals ma, that would be a very, very unusual thing to see, given that mass will not take a negative value for any of our purposes. So let's take a look at an example that utilizes vectors. So in a practical sense, let's look at a ship traveling 55 kilometers northeast on a bearing of 30 degrees to some point in space P. If the ship had traveled in a straight line, i.e. bearing 0 degrees north, how far would it have travelled? Now, this is a little unusual in terms of physics in that we're talking about cardinal points and we're looking at a ship travelling northeast. Normally, in a physical sense, and we'll see this when we deal with forces much more, we would ask for a direction, and that direction would always be an angle from the horizontal. In the case of a displacement vector, that always comes from the north point, wherever that is. For simplicity, I've actually redrawn this particular problem to place north as the horizontal. There's no reason we can't hold a map sideways, just to be consistent. So the question said that the ship was going to some point P. This was 30 degrees east. So we're looking at the ship moving at an angle of 30 degrees from the origin to this point P. So as with any physics problem, write out what we've got. We want to know if the ship had travelled in a straight line, how far would it have gone? Your diagram might look like this. As you can see, that gives us a 90-degree triangle. If this is 30 degrees, that means the horizontal angle here is going to be 60 for a total of 90 degrees. If we're looking at a right-angled triangle, that means if this is 60, this must be 90. Knowing this is 90 and this is 60, and all of the angles will add to 180, that gives us 30 degrees over here. As usual, we can apply our trig functions and we can look at our opposite, our hypotenuse, and our adjacent. We know that this distance here is 55 kilometers. Consequently, we should have chosen the sine function, which is the opposite over the hypotenuse. That'll give us sine of 60 is O over 55. Evaluating our sine function should give us this, and then saying that the opposite is then going to be 0.86603, our sine 60, times 55, to give us a simple 48 kilometers from the origin to a northerly point. That means had the ship just travelled straight north, it would have moved 48 kilometers in distance. So let's take a look at a little more of a florid example. So why am I picking on zombies here? Well, every time I try to do a problem like this, I say to people, well, you have to navigate, and you have to navigate, say, using a compass. And they say, I'll use my cell phone. I say, you haven't got your phone. People say, I've always got my phone. If I haven't got my phone, I've got a GPS, blah, blah, blah. So I have to come up with increasingly florid examples to make sure that you can't use any of these things. In this particular case, there's been a horrendous zombie apocalypse, and your phone and GPS have completely ceased to function due to the complete decay of society. And you have to navigate using a compass the old-fashioned way. Magnetic north is unaffected by this disaster. So you're looking for shelter and start walking at an angle of 60 degrees, once again northeast, at a total of 100 meters. The question now is, how far north are you from your starting point? How far east? We've then got a question about other bands, other people from your band of survivors. So let's take a look at the first part of the problem here. We have 60 degrees northeast, we have 100 meters. So the first part, number one, how far north are you from your starting point, and how far east? So what we're really asking for is the components of a vector of 100 at an angle of 60 degrees from the vertical. So if you were to draw this out, here are our cardinal points again, as per in the previous example. There's our point P that we've walked to, our angle of 60, and there's our 100 meter displacement. So we walk 60 degrees northeast for 100 meters, and here's the kind of scruffy diagram I would draw as opposed to the one we saw previously. Our theta of 60, our hypotenuse is 100 meters. This means our distance east will wind up being 100 sine 60, which will give us 87 meters in an easterly direction. Likewise, calculating our distance north will be 100 cosine of 60, which will give us 50 meters in the northerly direction. It's a relatively simple trig in this particular case. Parts 3 and 4 of this problem talked about the displacement from the starting point. So we just calculated our distance from the north using a 60 degree northeasterly travel. And now our question is going to state another member of our band is going to walk 90 meters east and then 50 meters north. So now we have the components of their vector displacements. What is their displacement from their starting point? And what was the second survivor's bearing from the origin? So in the first case, we knew the resultant vector and needed the components. Now we have the components and need to find the resultant vector. So once again, restatement of the question. What do we know? The survivor went 90 meters east and 50 meters north. We want the total displacement. So a quick scruffy diagram would show this. Here's our 90 meters east and our 50 meters north. And here is our total displacement. Of course, here our displacement will be the hypotenuse of our triangle. We don't know much other than the actual components. So this is a situation where we need to use Pythagorean theorem of a squared is equal to b squared plus c squared. If we apply this, that means our displacement s squared will be 50 squared plus 90 squared. The root of this will give us 103 meters, or about 100 meters-ish. The bearing now, we now know that we have a 50, 90, 100 triangle here. So theta now will be tan, inverse tan of course, because we want to find this angle, 50 over 90, using the opposite and the adjacent. This will be inverse tan essentially of 5/9, which will give us 29 degrees. So 103, about 100 meters at 90 minus 29, because what we've found here is actually the angle from the horizontal. So 90 minus 29, 61 degrees from the northerly point. Now that's an unusual situation. Most of the time in physics we could stop here and say this was a 29-degree angle. However, when we deal with bearings and navigation, we do have to go from the north point. So in this context we're saying 61 degrees. In most cases when you're calculating something like a force, 29 would probably be acceptable. Let's take a look at another example. A car travels 20 kilometers north and 35 kilometers 60 degrees west of north. Find the magnitude and direction of the car's displacement. So, car moves 20 kilometers north and then moves at a 60-degree angle in a westerly direction. So if we draw out our diagram just to understand what's going on, it'll look like this. There's our north, south, east, west cardinal points. Here's our diagram in more detail, giving us vectors A and B. We want the resultant vector R. So our angles here, here's our 60-degree angle, we'll have an interior angle theta, and we'll have beta here. We'll need the law of cosines to solve this problem. So the magnitude of R here, we can use the law of cosines from trig to get this for an obtuse triangle. So we're really looking at this and having a bit of a reminder about all of our trig of various different types of triangle. What will theta be in this case? Well, theta will be 180, essentially a straight line, minus the 60-degree angle that we have given to us, to give us 120 degrees. Applying the law of cosines, r squared will equal a squared plus b squared minus 2ab cos theta. We do need to rearrange this. Well, rearrange so much as root it, that r will be the square root of this. Substitute our values in, of which we have them all, and we should end up with 48.2 kilometers. Now, we really want to find the direction of R from the northerly point. We can get that one from the law of sines. So we're using everything in our toolbox here. So sine of the angle beta that was towards the foot of the diagram over B will equal sine theta over R. We want the angle. This will come from B over R sine theta. Substitute in, we get 0.629. Of course, we do have to finish this off and take the inverse sine of 0.629 to give us about 39 degrees. And of course, this angle is west of north. So let's take a look at what we have to do if we have to take the product of two vectors, A and B. So here we're going to take the scalar, or what's referred to more normally as the dot product of two vectors. So we have one vector, A, and another vector, B. Vector A is expressed as A, 0, 0. So it has a component in the x direction, but not in the y or z directions. Vector B has components in x and in y. Consequently, if we are to multiply A and B together, take A dot B, that means we cannot end up with any components in the y direction. There is nothing in the y direction for vector A. Consequently, if we take A dot B, we can take AX and BX, but AY and BY will equal 0. Therefore, A dot B is AX BX, which gives us A B cos theta. B cos theta is the projection of vector B onto vector A. The angle between the two vectors then will be cos theta, which will be AB, these are the vector quantities, over the magnitude of A and B. If we take a look at our notation, then in terms of vector algebra, what what is more normal than saying x, y, and z is to put things in what's referred to as unit vector notation and look at vectors as units of I, j, and k. That is a unit vector of 1 in the I direction, 1 in the j direction, and 1 in the k direction. So for a normal vector A in three-dimensional space, we would normally draw our three-dimensional vector as x, y, z. We would have our component in each direction, and there's our vector A. If we want to express this as a unit vector, the reason behind this being that what we really want to do is when we multiply two vectors together is make sure we're only ending up with components for that vector that are all in the same direction collected together. This means we can take our usual notation and now we can apply a vector, a unit vector of 1 in each direction. So instead of expressing things as x, y, z, or z, then we can express it as I, j, or k. So these following relations are the important ones in the dot product. So if we take a vector in unit vector in I and multiply it by another vector in the I direction, I dot I, we'll get a value of 1. Same for jj and same for k times k. If we attempt to take our unit vector and multiply it by a vector in another axis, so I dot j, I dot k, or j dot k, we will end up with a value of 0. We cannot multiply our vectors by another vector that is not in the same axis. This gives us our 3D unit vectors in terms of our I, j, and k unit vectors. So a unit vector is a vector of 1 in any one direction, which is multiplied by our standard vector. So a unit vector is particularly useful if we are multiplying vectors together. Usually larger groups of vectors are expressed better if we're using unit vector notation. So here we have A, which is going to be a vector in each direction. That'll give us a particular component in x, y, and z. If we're to express this, we'd have ax1, ay in 1, az would have a vector of 1. Sometimes you might see this notation. This is because Euler was the person who looked at unit vectors initially, and he tried to put his initial E onto it. So E x ax plus ey ay ez az. This is sort of the older notation, but sometimes you do still see this in textbooks. More normally, I will use I, j, and k, essentially a unit vector of 1 in the x, y, or z directions. So there's just a reminder of unit vector notation. So let's take a look at a general example of utilizing vectors. And this is a question from an exam. Here, Iron Man is searching a city and is going to fly from a rooftop at an angle of 30 degrees. You're going to find out shortly here that this is negative 30 degrees and moves a distance of 1 times 10 to the 2 meters. We're going to try and find the horizontal and vertical components of his displacement. So we've got negative 30 degrees, 1 times 10 to the 2 meters. Here's the situation. Iron Man's going to fly downwards here. There's our angle. There's our distance, d. So in terms of our diagram, this is what it's going to look like. He's going to fly along this direction A. He's going to have component AX in the X direction, AY in the Y direction, and he's going to go at negative 30 degrees. We're maintaining that negative for a reason. So there's the question straight from the exam. So what will our x component be? A cos theta. This is 1 times 10 to the 2 times cos of negative 30, which will give us a positive 86.6 meters. So he's gone 86.6 meters in the x direction. Now AY, the component of vector A in the y direction, will be sine theta, which will be 1 times 10 to the 2 sine negative 30, which will give us a negative 50 meters. Let's take a look at part B. Here we're looking at the other suit, the War Machine suit, and this is going to fly in the opposite x direction, giving a new displacement vector B with components negative 25 and by is 10 meters. So we've got an x displacement and a y displacement. What's the magnitude of the displacement vector, the resultant vector? So there he is, flying upwards now in the opposite direction, and what we have are our vectors in the x and y direction. So essentially similar to problems we've seen before. In the first case you had the components, find the vector. In the second case we have in the first case have the vector, find the components. In this case we have the components, find the vector. So b squared is bx squared plus by squared, as we saw before. So b becomes the root of bx squared plus by squared. Substitute in, and of course we'll get 27 meters. The 27 meter displacement vector, what's the direction of that displacement vector? And remember, put this in terms of angle. Well, the direction of that vector is going to be theta being inverse tan of by bx. That'll give us the inverse tan of 10 of negative 25, which will give us a negative 21.8. It's negative because he went the opposite direction to Iron Man. So technically this will be 180 minus 21.8, which will give us 15 degrees, or theta is equal to 158 if we look at it by quadrants. So let's talk about notation and vector algebra. If we look at a vector A of course can be defined by its magnitude and its direction relative to our coordinate reference system. For vector A in a three-dimensional space, it will have of course components in x, y and z. We can use unit vector notation of ijk to express this vector in slightly different terms. When we talk about a unit vector, what we're really saying is we will have a vector of unit length 1 in a particular direction of each component of our vector. So this means when we're doing vector algebra, specifically with multiple vectors, which can get quite complicated, when we're multiplying our vectors through, we will not end up multiplying by a vector which is incompatible. What do I mean by that? Well, if we multiply two vector quantities, we can only multiply in the scalar or dot product I with I, j with j, or k with k. So I.I, j.j, and k.k will give us 1. I.j, I.k, or j.k, i.e. a axis taking the scalar product with any other axis will give us 0. This means we can throw away a lot of terms that come to 0 and simplify our expressions very quickly and simplify our algebra. So we have to stick to these rules. But the scalar product of two vectors a and b will be a dot b, as I just explained, which will be ab cos theta. So in terms of unit vectors, this means we will have our same vector we always had. A will have components in 3 dimensions, x, y, and z here, but we will multiply by I, which should have these little hats on them, of course. Those little hats aren't on here because that's really difficult to do in PowerPoint, it turns out. So imagine those little arrow hats that you'll see in the book above the I, j, and k vectors. We can also express vector b in x, y, and z terms with I, j, k terms. So we're multiplying by a unit vector of 1 just to help keep our algebra intact. So a dot b will essentially be everything in the x direction times everything in
B's x direction plus everything in Y's direction, A's Y direction times everything in B's Y direction plus everything in A's Z direction times everything in B's Z direction. That will, of course, give us a scalar quantity. This particular formula is very useful if we're looking for an angle between our vectors, of course. So in terms of our vector dot product, let's take a look at an example. Here we have A, which is 3i plus 5j minus 2k. Vector B, 2i minus 2j minus 2k. So, doing this out longhand, if we take A dot B, we'll have 3i plus 5j minus 2k dot 2i minus 2j minus 2k. This means, if we throw away our zero terms, that A dot B will be 3 times 2 plus 5 times 2 times negative 2, I should say, minus 2 times minus 2. This, of course, will give us a negative term here for the 5 times 2. So this will be 6 minus 10, and here we have a negative times a negative, which will give us a positive 4. So this whole situation, this whole system, A dot B, will end up being 6 minus 10 plus 4. This will end up giving us a 0 value for the magnitude of these two vectors put together. So even though these two vectors are non-zero, when we find the dot product, we end up with a 0 magnitude. This would say that A and B are then not actually equal to 0 in terms of magnitude, but the magnitude of both of them is. This says that theta is 90 degrees, so A and B are perpendicular to one another. But what if we want to find the angle between two vectors? So here, let's find the angle between A equals 3i minus 4j and B equals negative 2i plus 3k. So the scalar product of these is stated as A dot B, here I've got the little vector notations, is equal to AB cos phi, where phi is the angle between the two vectors. So A is the magnitude of A, which will be found by our usual Pythagorean methods. So A is 3 squared plus minus 4 squared. Of course, this will end up being the magnitude, so this will root, this will equal 5. B, again, same deal, 2 squared plus 3 squared will give us a root here of 3.61. That allowed us to find the magnitude. Now, if we do A dot B equals 3i minus 4j dot negative 2i plus 3k, throw away the terms we don't want, we will end up with this. So the angle between the unit vectors I and I essentially is 0, and all of the terms will end up being 90. Because we'll end up with 3i dot minus 2i, 3i by 3k, j dot I will be 8, 4j, as you can see. So A dot B here will end up being 6 times 1 plus 9 times 0 plus 8 times 0 minus 12 times 0. Every term that is not by itself, i.e. 3i dot negative 2i here, is the only one that will be preserved. All the others, as proof here, come to 0, which gives us negative 6. So A dot B is negative 6. So this step here would not be necessary in a homework or exam to show, but I'm just showing explicitly that all these other terms disappear. So let's sub now our negative 6 into AB equals AB cos theta, or AB cos phi I should say. Here we've got 5 for B, we've got 3.61, sorry, AB cos phi. This will give us phi is inverse cos negative 6 over 5 times 3.61, which gives us 109 degrees. So those are some brief rundowns of how to do our scalar or dot products. Please take a look through the examples in the book and make sure you comprehend how to do this. People have often seen these particular examples in other classes and are usually familiar with vector algebra. This is more of a recap. So the other thing we can take is what's referred to as the vector or cross product between two vectors. So again, if we have vectors A and B and take the cross product of A and B, i.e. A cross B, we will result in a third vector, C. So C is A cross B. The magnitude of vector C will be AB sine theta. That's where theta is going to be the angle between A and B. And what does that really mean? Well, the cross product is one of those things that's going to come back later. So we're not really going to employ it too much here because we're going to use it in context later on when we're talking about such things as torque and angular momentum. And those are the two places this will really come back to us when we deal with mechanics. So the magnitude of C, as we said, is AB sine theta. And you could look at the parallelogram rule and figure this out. But there's a simple rule when we deal with our cross product. If vectors A and B are 90 degrees to one another, then vector C will be 90 degrees to both A and B. That means if A is in this direction, B is in this direction, and we take A cross B, we will end up with vector C coming straight upwards 90 degrees to both of these vectors. Likewise, if we take negative C here, this will be B cross A. So changing the order in which we actually process our cross product, so A cross B gives positive C, likewise B cross A will give us a negative C. So in vector terms, if we take A cross B, it'll be in the positive direction. If we take B cross A, C will be in the negative direction. And as we'll see when we get to dealing with torque, this is actually shown by the right-hand rule. So the product of two vectors is the vector or cross product. And this is a case of looking at torque. So in torque, which is a twisting force, so if this is a disk and we wanted to find the twisting force about this axis, we would take the radius r and look at the force F. So we would have torque would be R cross F. Where is the force applied? At what distance? So torque is R cross F or RF sine phi. Phi being the angle between R and F. This results in torque rotating an object about an axis that's perpendicular to both R and F, 90 degrees to them. So you end up with torque in the axis of rotation in the previous case. Remember, our vector product is not commutative. So unlike scalars, the order in which the vectors are multiplied is very important. So if A is parallel to B, theta is 0, 180, then A cross B is equal to negative B cross A. If A is 90 degrees, then we end up with A cross B. If they're 90 degrees to one another, then we end up with A cross B being equal to 0. A cross A is 0, and A cross B essentially is just the magnitude of A times B. Our vector product, of course, is distributive, so A cross B plus C will end up being A cross B plus A cross C. You would have to distribute A through all the terms in this bracket. So you should be able to see the differences and contrast them with the scalar product a little bit. Now, where the vector product severely differs from the dot product, or cross and dot product, of course, is that in the vector product, in the cross case, I cross I, J cross J, and K cross K are 0, whereas our axis crossed with any other axis will give a non-zero result back. So I cross J gives us negative J cross I. This is the opposite here, which will give us K. J cross K gives us negative K cross J, which is I. K cross I is negative I cross K, which gives us J. So if we take the cross product of any two directions, any two axes, we end up with the other axis, k cross I gives us j, j cross k gives us I. But any axis, any unit vector in any one axis that you take the cross product with of a vector in the same axis will give you 0. And here's the contrast with the case of the dot product. So the signs are interchangeable in our cross products also. So I cross negative j could be negative I cross j. Or a cross minus b could be equal to minus a cross b. And there's sort of an example here. Here's a, here's b, 90 degrees to one another. The result of a cross b will be 90 degrees to both b and a. So simply, a cross b is magnitude of a times magnitude of b times sine of theta, where theta is the angle between a and b. The simplest case, of course, being 90 degrees. So let's take a look at an example. Here we have a minus b cross a plus b. This will be a cross a plus b minus b cross a plus b. This will be, if we expand it out, a cross a plus a cross b minus b cross a minus b cross b. Of course, remembering our rules, this will be, if we throw away anything that is by itself, so a cross a and b cross b, we will end up with a cross b plus, essentially, b cross a, which will give us 2a cross b. Now, something to note when looking at problems involving the cross product is what are the setup variables. So here, two vectors lying in the xy plane are given by equations. A is 2i plus 3j, b is negative I plus 2j. And we're just going to simply find a cross b. So there's our situation. This will equal 2i cross 2j plus 3j cross negative I. We're throwing away all of the other terms that we don't need. This will give us 4k, I cross j is k, j cross negative I is also k, will give us 7k. So all occurrences of I cross I and j cross j is equal to 0, and if you wanted to, you could expand all of those out if you wished. I haven't done that here, just so I can have some space. But now let's find b cross a. So b cross a with the same vectors is negative I plus 2j crossed with 2i plus 3j. This is negative I cross 3j plus 2j cross 2i. Simplifying is negative 3k minus 4k, which is negative 7k. So you can see that a cross b will essentially be negative of b cross I. Again, we can take 3i minus 4j here, and the second vector of b is negative 2i plus 3k, and say that c here is 90 degrees to both a and b. So some new vector c will come from a cross b. So 3i cross negative 2i plus 3i cross 3k plus 4j cross negative 2i plus negative 4j cross 3k. This one's in a little more detail. Now c is AB sine phi, where phi is the angle between the vectors. The first term is phi equals 0, everything else will be phi equals 90. So c is going to be negative 6 times 0, because those are I cross I terms, plus 9 negative j plus 8 negative k minus 12i. This will give us 12i minus 9j minus 8k. So we've dealt with torque, we've dealt with a few examples of our dot and cross products. The only other place we could possibly see this, and we will see this later on in terms of the physics we're doing, would be in terms of angular momentum. And this is a good example, because think about spinning a coin. If you put a coin on a desk and spin it around, what will happen? You will apply a velocity, or more accurately, a momentum at the corner of that coin. if you apply that at essentially 90 degrees, you will add to the radius of the coin, of course, you will end up with V 90 degrees to R. And P here is M times V. That will end up with L, the angular momentum, coming out of the top of the coin. And you can see this as the coin spins around an axis. So L will be mvr sine phi. So or L is equal to R cross P. So here's our example. If this was a coin, we would apply a velocity here to our mass at radius R, resulting in L being 90 degrees to R and 90 degrees to V, and coming out of the top of the coin and causing it to spin around an axis.